Hi there, Addie. I think you're going to like today's lesson. We're going to do lesson 12, which goes over angles and diagonals in polygons. It's actually kind of fun. That part of it is really fun. And then we'll talk quickly about the proof of the chord tangent theorem. But before we do that, let's look at this little meme here. Me loses all money in Monopoly. Oh, I hate Monopoly for that reason. Me, don't freak out. It's just a game. What would Jesus do? Me thinks of what Jesus would do. Remember that story? That is a story in the Bible where he turns over the tables because the money changers are at the temple there. So there you go. Probably still shouldn't do it in Monopoly, but something to think about. All right, let's talk a little bit about polygons. You'll remember that this one on the left is a concave polygon. It has this indentation that's like a cave. This one on the right is a convex polygon, so all the angles are going outward from the center. One thing that they want you to know is that if you look at the number of sides of a polygon, so this one has 5 sides, this one also has 5 sides, that means that that's how many corners there are. That's how many vertices there are. So the number of sides is equal to the number of vertices, okay? So that's kind of interesting. And then at each vertex, let's look at some of these vertices. At each vertex of both a concave and a convex polygon, there's an angle. There's an angle that's inside the polygon and an angle that is outside the polygon, right? The sum of these two angles at any vertex, like in any corner, is going to be 360 degrees, obviously, because it kind of makes a circle. Convex polygons, so not the concave polygons, but convex polygons, they have something different called an interior and an exterior angle at each vertex. And there's going to be actually 2 exterior angles at each vertex. So let me show you how to make an exterior angle. So if the interior angle is this guy, let's look at this bottom right corner. That's the interior angle. The way that you make an exterior angle here with the convex polygon is that you extend one of the lines, okay? And then the exterior angle is the rest of that angle that goes to the line if it were extended. So that's one of the exterior angles right here. And you can see, we're going to talk about it, that the sum of this interior and this exterior angle has to be 180. Of course it does, because it makes a straight line, and a straight line have an angle of 180. Like if you're driving down the road and you go, make a 180 degree turn, it wants you to turn around and go in the other direction. That's a 180 degree turn. All right, there's another exterior angle at this corner, even at this same corner. And that's if you extend this line and you push it out like that, I didn't draw it very well, it should be a straight line, something like that. And then this is the other exterior angle. But again, the interior and this exterior angle are going to add up to 180 because that's another straight line. Okay? So cool. So, and every corner has one. See, right there and right there. You can make this exterior angle and that exterior angle right there. So, and of course, since they form a straight line, the sum of the interior and the exterior angle is going to be 180. All right. So this triangle, let's look at this triangle. This triangle below has 3 sides, obviously, 1, 2, 3, and 3 vertices, okay? And when you add up the measure of the interior angles, they're all going to be 180 degrees. You know that already. Add the angles of a triangle, any triangle, it doesn't matter. It can be obtuse, it can be, any triangle. If you add up all the angles, they always add up to 180 degrees. Turns out you can also find the sum of the interior angles of any polygon like this. So ignore these lines on the inside and just look at this polygon. Can you add up the interior angles there? And it turns out you can if you just triangulate the polygon, which is kind of interesting. Triangulate, that's kind of a new verb, triangulate. That means to turn it into triangles. That makes sense. That's kind of cool, right? So the way you turn it into triangles is you make these lines. If I make a line there and if I make a line there, now this complex polygon is 3 sets of triangles, 3 triangles, right? And what happens is that this triangle, let's do this triangle first. This triangle, if you add up the interior angles of that triangle, it's 180 degrees. And then this is a new triangle. If you add up the angles of that interior triangle, it's 180 degrees. Same with this triangle, 180 degrees. So if you take 180 plus 180 plus 180, the total is going to be 540 degrees. And it turns out that that is the sum of all of the angles inside this complicated pentagon. Pentagon, right? 1, 2, 3, 4, 5. Yeah, it's a pentagon. So there you go. A pentagon, a five-sided polygon or a pentagon can be triangulated into 3 triangles. And so you know that the interior angles can add up to 540 degrees because it's 3 triangles put together. In a minute, we'll figure out how many triangles you can make out of something and sort of a formula to do that. Okay, let's look at this dude, this little dude walking around this shape. Okay, so the shape that they want you to look at is this shape. Ignore all those other lines for now. That's the shape of the polygon. All right, the sum of the measures of the exterior angles now, of any convex polygon is 360 degrees. So that is interesting. It can have as many sides as you want. But if you add up just in one of the directions, like make this into a straight line, here's an exterior angle. Make this into a straight line, here's an exterior angle. And then make this, and the way that you do that is you pretend you're a dude walking around the shape and just make exterior angles as you go. And if you do that, it doesn't matter what the shape is, what kind of polygon or how many sides it has. If you keep adding up the angles of all these shapes, they're always going to add to 360 degrees. And you can remember that because this guy made a full circle. He went 360 degrees. It's just kind of breaking up that 360 degrees into these angles. Like he goes straight, he turns. He goes straight, he turns more degrees. So it's not like a perfect circle, but it makes sense that it would total 360 degrees if you're going around the outside and making a circle out of it. Okay, for this shape, you can see that there are 5 diagonals. Okay, so here's the shape. 1, 2, 3, 4, 5. It's a pentagon. We've made 5 diagonals inside of it, inside this convex pentagon. And let's say that you wanted to figure out how many diagonals can you make anytime you have a shape like that. This is what you do to figure that out. Okay, let's look at this shape. And the question is, how do we know how many diagonals can be drawn? And here's a way to do it. Let's say we're starting with the letter B and we're going to draw diagonals that all emanate from vertex B to all of the other vertices, okay? So if you do that, you actually don't need a diagonal to C because that's just the outside of it. You don't need a diagonal to A because that's just the outside of it. And you don't need a diagonal to itself because it's itself. So the only diagonals you can emanate from B go to D, E, and F. And they want to make a formula for that. And so if we have n number of sides, because we want this to be true for any polygon no matter how many sides it has, how do we figure out how many diagonals we can draw? Well, the first step is that we figured out we can draw n minus 3 diagonals from one point. Why is it n minus 3? Because the number of vertices is the number of sides. So if we have n sides, then we have n other corners. But you're going to not do 3 of those corners because you're not going to count C, you're not going to count A, and you're not going to count itself. So no matter what it is, no matter how many, we could add other points here. You would draw another one there, right? But it would always be n minus 3 because you're not drawing to itself or to its neighbors. Okay, but then you could also do that from any other point. So then if we start with D, you could do points like this. Right? So it's also n minus 3. We have to multiply that by the number of sides there are. Okay? Now, there's one other thing in this formula for figuring out how many diagonals we can draw. And that's this point. the point is this. If we already drew one from B to D, then we don't need to count the one that we drew from D to B because it's the same line. So by that logic, since we don't want to double count each line because each single line has 2 vertices, in order to not double count it, then we have to divide the whole thing by 2. And this is the formula for number, I'll just say number of diagonals. Now they don't want you to memorize it. I'm not gonna draw a cloud around it that means that you have to remember it. They just want you to know how to derive it and how they got it. Okay, so let's see if it works here. Oh, that's the one we got. Yeah, they just want you to figure out how these formulas are made. And so that you can start thinking about how to make an expression that will give you the answer to some question like that. Here's another one to look at. Let's say we have a polygon. How many triangles can we make out of it? So that was when we go to triangulate a shape, how many triangles do we make and we know that we got it right? So to figure this part out, you can realize that a convex polygon can be triangulated into n minus 2. N is the number of sides. So let's try it and see if it works. A triangle has 3 sides. 1, 2, 3. 3 minus 2 would be 1. So you can make a triangle into only one triangle. That makes sense. Let's look at this quadrilateral. This has 4 sides. 4 minus 2 is 2. You can make it into 2 triangles. 1, 2. Okay, sweet. So what about this complicated shape? This has 6 sides. This is a hexagon. And if we do n minus 2, it's 6 minus 2, which is 4. You can make it into 4 triangles. Okay, so a convex polygon can be triangulated into n minus 2 triangles. And since the sum of the angles of the interior of a triangle is 180 degrees, you can also use this formula to figure out, well, how many degrees are there going to be inside any shape? Because this is the number of triangles you can make. So if you multiply the number of triangles you can make times 180, I like it better when the 180 is on the other side. Let's put it over here. 180 degrees times n minus 2. This is the formula for how many degrees are in any convex polygon as long as it has n sides, right? So I'll put degrees, or sum of the interior angles, degrees inside a polygon. Inside a polygon. Okay. Cool. Does that make sense? Let's do an example and see if it makes sense. Oh, this is what I just said. Bluey and Bingo are fascinated by this. The sum of the measures of the interior angles of a convex polygon of n sides is n minus 2 times 180. All right, let's do an example. Here, they want you to find the sum of the measures of the interior angles of this shape and the exterior angles. Okay, so the interior angles, they gave you a shape. It has 1, 2, 3, 4, 5, 6, 7 sides. It's a heptagon, right? Is that what that is? Pretty sure. Okay, and then there are a couple ways that you can do this. You can just use that formula that I just gave you. This is the part in the book where it was kind of funny, where it said some people like to stick numbers into formulas and turn the crank. And the way you would stick a number into the formula is say, well, I want to know what's the interior angles, sum of the interior angles. And I know the formula is n minus 2 times 180. So then I just plug in n is the number of sides. I just figured out it's 7. So 7 minus 2 times 180, and you get 900 for that, because 7 minus 2 is 5. 5 times 180 is 900. Or if you forget that formula, like you're taking the SAT or the ACT test and they give you this problem and you forget the formula, that's fine. all you have to do is make it into triangles. And once you make it into triangles, you count the triangles. 1, 2, 3, 4, 5. And you remember that every triangle, the interior angles add up to 180 degrees. 5 times 180 is 900. So even if you forget the formula, that's fine. Cool. We're done with that. That's the answer to A. Now, what about B? They want to know the exterior angles. The exterior angles is when you're a dude and you're walking around the whole circle. And all you do is you walk straight, you add that exterior angle. Then you walk straight, you add that exterior angle. Okay? You're the dude walking around. And you don't even have to add them up or think about it, because you know if you start here and you walk all the way around, you're going to make a full circle. So the answer to B is 360 degrees. Sweet. Okay, the next part of this lesson is the chord tangent theorem, and it proves the chord tangent theorem. All you have to remember here is that when you have like a lyra, remember the lyra, and you've got the legs going like this, okay, the inside angle, like I called it the crotch angle, is 30 degrees, and then this arc has a measurement of 60 degrees. And this is always going to be half of this. And they kind of go through, if you want to read about it, you can, on proving that. Like, how can you prove that mathematically? And there's a way to prove it, and it's on page number 93. But guess what? I ain't going to do it. So go ahead and start your problem set that starts on page 95. And if you want to read that proof, you can. But there you go. Have a great day. Love ya. Bye.